Hi, so last lecture we discussed motion diagrams and how we describe motion. And if you recall, we came up with essentially three words we're going to use to describe motion. One was position, one was velocity, and one was acceleration. Um, uh, Velocity was how position changes in time, and acceleration was how velocity changes in time. And we also discussed how to visualize motion. One of the ways we can do that is with what's called a motion diagram. Today, what we're going to go into is we're going to actually build on that concept of motion diagrams and try to add a little bit of quantitative reasoning or quantitative analysis to that. So essentially what I'm going to do is let's work through an example of a motion diagram and add a bit of numbers to it and add to these definitions or how we think of position, velocity, and acceleration. So let's imagine we have a car that's speeding along and it's driving and it slows down and comes to a stop, right? So the motion diagram would look something like this, right? And we have this happens at t0, t1, and T2 and T3. All right. And as we discussed last time, we now have an indication of these. We can see it's slowing down. The spacing between these points is getting smaller. Each one of these images was taken, these are essentially sequential photos taken on top of each other. We'll say, let's just, because it's an easy number to work with, we'll say that they were taken 1 second apart. So T1 would be equal to 1 second, T2 would be equal to 2 seconds, and T3 would be equal to 3 seconds, right? Now, one of the things that we need to do if we're going to be describing these things numerically is have some sort of coordinate system and reference frame that we're going to describe these through. So in time, we usually start time at 0 at the start of our problems. So that has an origin as we started at time of 0 seconds, which seems pretty natural. But we also need an origin for our position or a space that we're describing the system in. And the way we can add that to a motion diagram for a problem like this that's one-dimensional is essentially just draw a line that is going to be represented of the position, the direction we're talking about, and we'll call it X, and we'll label this positive direction as being the X direction. And now we need to choose where the origin of this direction is. And one of the nice things is we're free to choose the origin wherever we want. It will not affect any of the physics or any of the description of this. But just for the sake of simplicity, let's call this our 0 point, right? So now, if we go through and continue on with our motion diagram, where we have this is x0, this is x1, this is x2, and this is x3, the positions of our images in our motion diagram, we can actually put numbers to this. X0 would be 0 meters, x1 would be whatever this value is. Let's call it 11 meters. X2 would be even further along. We'll say, I don't know, 17 meters. And X3, we'll say 18 meters, right? So once we've defined this, coordinate system, this X direction, and we've defined our origin on it, we now can put numbers to what our actual positions are. We know where they are in our reference frame, in our coordinate system. And now we can continue on with what we were doing with our motion diagrams. And if you recall, the velocities can be represented as arrows connecting these dots, right? Each one was there. So this would be V1, this would be V2, this would be V3, right? Now, our definition for velocity was the change in position, which we'll call delta x. Delta is typically what we use for change in position. and over the change in time, how far the change in time was. So if we wanted to add numbers to this, we can do that. We have v1 is equal to delta x over delta t, and in this case, the change in x was just the final x at the end minus what it was at the initial, and likewise, the change in time is going to be t1 minus t0. And if we plug in the numbers that we have just because we've chosen our reference frame, this is going to be 11 meters minus 0 meters over 1 second minus 0 seconds, or this whole thing ends up being 11 meters per second is what our V1 is. And if we do the same thing for V2, we end up with 17 meters minus 11 meters over 1 second, because 2 minus 1. This ends up being 6 meters per second. And finally, V3 is just going to be 1 meters per second. 18 minus 17 gives us 1 meter divided by the 1 second time difference. So you can quickly see we have these velocities going that way, and we can put numbers to them just by going with our definition. The change in position over the change in time gives us those things. The last thing we did in our motion diagrams last time was we discussed acceleration. And the acceleration was the change in velocity over the change in time. And if you remember how we did that, that's going to be v2 minus v1 over delta t. And v2, if we draw it, looks like this. v2. And v1 is a much longer arrow. But if we want negative v1, this negative changes the direction of that v1. So negative v1 looks something like this, where that's negative v1, right? It's the same, it's this arrow here, just in the opposite direction. So if we wanted to go with what our acceleration is, it's where we started here to where we ended, and that's the acceleration, that's the delta v, which we represented as our acceleration between v2 and v1. So we would draw that, let's use black again. This would be what our representation of A1 looks like as we change from V1 to V2. If we wanted to calculate that, A1 is just going to be V2 minus V1 over T, over our delta T of 1 second. And since we have V1 and V2, this ends up being 6 meters per second minus 11 meters per second, all divided by 1 second, the change in time between those. And this ends up being negative 5 meters per second squared is our acceleration. Now, this may, depending on your experience with prior physics or anything, this negative sign might seem weird to you, but it makes total sense. In these motion diagrams, the direction of these quantities is determined by a sign, right? So one of the things that we have to be careful with is position, velocity, and acceleration. All are all quantities that include a direction with them. They're what we call vectors. So the positions are all positive. They are, if you were to draw an arrow from your origin to those positions, they would be arrows pointing in the right direction. That would be the arrow representing x1. The next arrow would just be longer. But they're all pointed to the right, which we've defined as the positive direction in x. So they're all positive numbers. Likewise, the velocity vectors. The velocities are all pointed to the right. So those are going to be positive quantities. And when we do the calculations, we get positive numbers, right? The accelerations, because it's slowing down, are actually pointed to the left. These velocities are getting smaller in the positive direction or larger in the negative direction if you want to do it. So that's causing this negative sign here. And when we go through the numbers, it comes out as a negative number. And if we were to, just qualitatively think about it as drawing arrows like we did in the past, again, they're pointed to the left, which indicates a negative number. So those are very important and very sort of subtle things with these motion diagrams that are really just sort of highlight the usefulness of it. Um, so stepping back, what we have is this nice visual representation, and you can slowly see by adding this coordinate system x to it, um, we can actually put some numbers to it and start to see how we're describing motion quantitatively in these problems. And that's pretty much it. Next video, we're going to discuss, will be a brief one on, units and significant figures and things like that. Then we're going to move into graphical representations of motion and another way we can think about motion and kinematics.